First, I might want to do Python OK. Oops. Make sure I have Python 3 installed. Max Wolf. Uh-oh. Now you'll know my email. Okay. So, unable to complete backup, whatever. These tests are not useful for me, right? Right now, I'm just sort of testing basic functionality. So what I want to do is I'm going to go python-i quiz2.py, right? Okay, so now I've loaded up this file into Python, and I'm able to sort of run through my doc test as is. Alright, well this makes sense. I'm getting to the end of the file because I'm not hitting any of my base cases and I haven't defined my recursion yet. So, but let's see if I can make change for something that I want to make change for, right? So if I'm given just a single penny and I want to make change for 0, I expect this to return an empty list. Okay, perfect. That's exactly what it does. Now see, what if I don't have any coins left? Oh, okay, that's weird. This should return an empty list even if I don't have any coins, because I've successfully made change for 0. These two shouldn't be different, because I don't need any coins, right? So maybe that points to my base case not being in the right place. Okay, so my base case is amount equals 0. I think it makes sense for this to be up here, right? So I like to think of trying to put my success base cases at the top, because if you're successful, then you want to know when you're successful, right? You're going to be successful far less often than you'll fail. Most of the time, you're going to try and be making change for something that, you'll eventually get to the end of your recursion and it just won't work out. So we definitely want these successful recursive branches to bubble up. So, okay, great. So return blank. So now let's exit this. I've reloaded the file into Python. Oh, that's not what I wanted to do. Make change for this. Okay, that's fine, but what if I make change for 0? Okay, good. Now if I get an empty list, okay, cool. Alright, so I'm expecting an empty dictionary to also return an empty list. This is what I get. That's great. Okay, so I feel pretty comfortable with these base cases. These feel like good base cases to me. So maybe let's start thinking about how we might do our recursive branches. So we looked a little bit at the homework, and the homework 3, where we had count change, it seemed like one of our recursive branches was sort of use coin, right? We wanted to actually use this coin. Oh, and the one reason I'm not defining some helper function here, which I think was sort of something that I saw occasionally in office hours, is because it looks like I already have enough information to do the recursion here, right? So there are two things I'm likely to be changing in my recursive steps. One are the coins that I'm allowed to use, right? So, after I use a coin, I shouldn't still be able to continue using that coin. And another one is, the other thing that I might want to change is the amount, right? So if I'm using a coin, I might want to actually decrement amount. So here it looks like I have enough information and I don't actually need a helper function to sort of finish this problem. If I didn't have coins, then it might make sense for me to define a helper function. Okay, so I've decided I'm going to use this coin. I'm going to use the smallest coin that I have. So let's have a make change. Let's do a recursive call on make change. We said we're going to use the smallest coin, right? So I'm going to say that I'm going to use the smallest coin by decrementing amount. So I'm getting closer to my base case, which is amount equals 0, or amount is less than 0. And now I've decided I've used the coin, so I need to pass in rest as my coins, right? So rest is going to be a dictionary of coins that has one fewer coin in it. Okay, so I'm using this coin. That's one of my base cases, and let's go ahead and write our second base case. So the second base case is I forget the coin. So let's call this forget coin. I'm going to make change, and I'm not going to decrement it from smallest because I'm not using it. But I still want to use rest because I've decided I'm going to forget about using that coin. I'm not going to use that coin. Okay, so we have a forget coin. And this actually, you'll see this comes up sort of right here. So here we make a set of coins that's 2, 2. We have two value coins, 2 3 value coins, 3 4 value coins, and 1 5 value coin. And when we're trying to make change for 25, if we didn't forget about the second 2 here, if you want to draw it out yourself, it'll make it a little bit more clear. If we were to try and use both of our 2s, in this list, which is what we're like preferring, right? We're trying to prefer the lowest value coins and using the lowest value coins as many times as we can. Then you'll end up, if you use 2 and then 2 and always use 2 and 2, then you'll end up making it's unsolvable. You actually can't return a correct change amount for 25, given that you've used this coin and then another 2 coin. Okay, that's just something to keep in mind. This is sort of the logic behind why we need to forget coins. Whenever we're looking at a single coin, there's only 2 options. We either use the coin or we don't use the coin. And if we don't use the coin, we want to forget about it and not use it, right? So not keep track of it. So this is what rest is doing as well. Just some background to figure out, what the logic behind having a use coin and a forget coin is. Okay. Alright, so use coin and forget coin should be 2 lists. Now, which one do we want to prefer? So if use coin is going to be the one that used the smallest coin, and so we always want to prefer the list that used the smallest coin. So let's see if this is not equal to none. Then what we'll do is we want to return a list. We've decided we have used the smallest coin, right? So we're going to use coin plus use coin. If we don't include the smallest, we don't actually build onto our recursion. So use coin is going to return the change list for whatever. It's going to return the change list for some decremented amount and some smaller set of coins. But we've decided we're going to use smallest, so we need to include this in our list that we're returning. Okay. So now we have another thing. If forget coin does not equal none, then we want to just return forget coin, right? And then otherwise we want to return none. So if use coin does not equal none means we successfully found a way to use our smallest coin. So we've called make change on amount and smallest, and it's done the whole recursion, a way to successfully use that smallest coin that we decided we were going to prefer. And so if this is not none, that means we've been successful. If it is none, then we failed. That left branch is sort of all failed. I encourage you to go home and draw the recursive tree for this. It'll probably make things a little bit more clear. And then otherwise we're going to see whether or not forget coin is successful. So our backup strategy was that we forgot about the coin and then continued to do our recursion without using that coin. So if use coin is unsuccessful, then we're going to check to see whether or not, we can call this an else if even, whether or not forget coin was successful, which means it didn't return none, and then we can return forget coin. It's important here that we use not equal to none instead of just if use coin, because it might return an empty list, and we don't want that recursion to sort of just say that we failed even though we didn't fail. Alright, so now I'm going to test it in OK. I'm going to test it actually in my -I. Oh, great. Okay, cool. So it's working for these base cases, or for these like sort of pretty easy stuff. Yeah, we're getting return 1. I'm just copy and pasting this stuff from the doc test, which is probably not the most efficient way to do this. So we've made some coin list that we're going to say is like a big bank of coins. So now I'm making change for 4 coins. We can sort of look at what coins we used. So it looks like our left branch was what ended up being successful. So we have 2, 2. Let's put some, maybe we can put some print statements in here to figure out what we're at each stage. So I'm going to print as I start. Here I'm going to print the coins that I have. I'm going to print coins. So amount, and then I want to print coins. Just so it's clear to see what the recursion sort of looks like. Oh my gosh. Wow. It's a lot of stuff. Okay, so let's see what happens. So we started with 4, with an amount of 4, and we started with this many coins. And it looks like we took our left branch. Oh, well, this is interesting. We took our left branch and decremented our number of coins that we had by 2, right? Then we also forgot about that coin. So we have sort of two options, where you either can remember that coin and use it, or forget about the coin and keep going. This is the entire right side of the branch of forgetting about some coin, right? Forget about the coin, forget about the coin, forget about the coin. Oh, you know what? Interesting. Okay, so I know what's happening here. The reason that we don't see this is because we don't print. Yeah. So the reason we're seeing this whole tree is because I've actually put this forget coin. I'm doing the whole recursive tree either way, and it might be easier for me not to do that. It's going to be a little bit more efficient for me to only calculate the right side of the coin if I need, or the right side of the recursion if I need the right side of the recursion. So you see here, I can see that I've taken the left side of the recursion and started that. And actually I think I've finished it in this one. And then what I do is I follow the whole right side of the recursion, and I keep forgetting about coins, right? So I'm going to forget about all these coins. It's going to hit base cases all the way down. And then I can fix that just by moving this right base case, or this right recursive call, behind my successful recursive call. So I'm going to, if my left branch is successful, I can just return out and I don't need to calculate my right branch. So it's interesting how important, how tremendously important having the base cases in the right order is, and having the recursive calls in the right order as well is. So if you're having trouble, and if you were having trouble, you might have noticed that it might make sense for you to look back at your code and figure out whether or not you had this successful base case at the front, whether or not you had it somewhere down here. Okay. Well, so I think I'm pretty confident in this. So let's go ahead and test it with OK. Okay. Well, it looks like the only thing I'm failing now are these change machine things. Okay, which makes sense because I haven't implemented it yet. All right. If people have questions about this, sorry I was so rambling. If people have questions about this, feel free to post a comment or come to office hours. Hopefully this made the make change question a little bit more straightforward. You can sort of see I had my two recursive calls, I either use the coin or forget about the coin, and then I made sure to be super careful about my base cases, right? Covering all your bases for your base cases is really important. Just going to put these together to make that a little bit more clear. Okay, cool. Saving all the time,